Hi everyone, so in this video I want to talk a little bit more generally about what statistical inference is and where sampling distributions fit in this process. And so when we talk about statistical inference, this is the process of drawing conclusions about an entire population based on information in a sample. And so for example, the permutation test, hypothesis tests that we've been looking at are a type of statistical inference because we're using one sample to try and gauge two competing claims about the population. And so let's just think about the underpinnings of how this process goes. So we have a population and we pick a sample out of that population. And what's important here is that we are going to choose these samples randomly. And so if I pick a random sample out of this population, then the sample is going to closely resemble the population, just smaller in number. So any characteristics of the population should be similarly reflected in the sample data that we pick. And so how inference goes is we have one sample and we're trying to say something about the population. And so what I want to talk about today is if we happen to know what the population looks like, what would the distribution of these sample statistics look like? And that's what we can get from a sampling distribution. And then once we have this sampling distribution, we'll reverse the process, which is how could we use the sampling distribution if instead of knowing the population, we only know one sample? How can we make some inferences about the population? And just to comment on some points about this sampling process. Well, when we pick the sample randomly, again, we expect the sample to resemble the population, closely resemble the population. However, because different samples are going to consist of different individuals, maybe some other sample chooses some of these individuals randomly, we're going to have some difference in these sample statistics. They are going to vary a little bit from sample to sample. And so the question is, when we're using samples to make predictions about the population, how can we account for this variability in the sample, right? Since my sample is going to be close to the population, but not perfect. And so on the next slide, let's see how we can use repeated sampling to construct a sampling distribution to get some idea of how big this variability is. So when we construct a sampling distribution, this is a distribution of sample statistics. So things like means and proportions are common sampling distributions to set up. And so we're going to independently pick a whole bunch of random samples, and they all are the same size from the same population. So our samples are independent and random, all coming from the same population, same size. And so we've got, let's say we have a population of men, and let's say the mean height of all of the men in the world is 70 inches. And let's consider what the sampling distribution for mean heights would look like if we pick random samples, each size n. And so most of these samples are going to be pretty close and resemble the population, which has a mean of 70, but they're not going to be perfect. So maybe the red one is a little bit below, and then the sample x bar 2 is a little bit above, and maybe x bar 3, well, that's really close to 70. And we can fill this distribution in and in and in for more and more values. And so we do this many, many times over and over again, and that gives us the sampling distribution. And so they're going to show us exactly how much variability is reasonable. So I don't know what these extremes might be. Would it be reasonable to get a sample mean height that's 60 inches tall, 90 inches tall? So that's what the sampling distribution is going to be able to quantify for us, and that's really going to be critical in the statistical inference process. And so this measurement of the variability of the sampling is what's called the standard error, and the standard error is just telling us the standard deviation for the sampling distribution. But we call it the standard error because it's capturing something different than variability from individual to individual in the population. It's telling us how much variability is there in sample statistics calculated from the population where we have samples all size n. And so this standard error, because it's special, we give it notation, SE, to stand for standard error, and this would denote the standard error for some sampling distribution of test statistic. So that might be a mean, sample mean, or sample proportion we'll see in a second. And we'll see some instances where we're unable to calculate the precise value of the standard error, but we might come up with an estimate for it. And so when we're coming up with predictions, estimates for values, we put hats over them. So this would get denoted with a standard error with a hat on top of it. And so we've done some work looking at sampling distributions for the mean, and we discussed the central limit theorem in that instance. Let's take a look at what happens if our sample statistic is a proportion instead of a mean. So let's consider the following population. So we're going to consider our population all students currently enrolled at CU Denver. And it's pretty close that 60% of all students at CU Denver are undergraduates, 40% are graduates. And what I want to do is construct a sampling distribution for the proportion of students in a sample of size 100 that would be undergraduates. So let's think about how we could calculate the expected value of this sample proportion. So the first thing I can do is just note that P hat would be what are how many students in this sample are undergraduates, and then divide that by the size of the sample 100. So X is how many students out of the 100 students in our sample are undergraduates. And since we're picking these samples independently from each other, this random variable X is actually going to follow a binomial distribution where we're repeating 100 trials. Each trial is picking a student, and each student that we pick has a 60% chance of being an undergraduate. And so now we can calculate this expected value exactly using properties of expected value and the binomial distribution. And so in particular, if you recall, we can pull out constant multiples from inside the expected value. And then we know that the expected value, since this is a binomial distribution, that expected value is equal to n times p. And now we can cancel those n's, and what's left is just p. And so this makes sense that the expected value for the sample proportion is equal to the population proportion, which is 0.6. So hopefully this intuition makes exact sense here, that if I pick a random sample of 100 students, I should expect 60% of them to be undergraduates. So let's do a similar process to calculate the variance of the distribution of sample proportions. So I'm going to calculate the variance of this random variable x, which is given by this binomial distribution, divided by n. And with variance, we have a similar property that we can pull out constant multiples, but when they get pulled out, remember, they get pulled out by a factor of squaring it. So we would have 1 over n squared times the variance of x. Since x is binomial, we have a formula for calculating the variance of x. It's just n times p times q, where, recall, q is the probability of a failure. So that's 1 minus p. And now, again, we can cancel the n's out, and we see that formula for the variance is therefore p times the probability of a loss or of a failure, which would be 1 minus p, and then we divide that by n, since one of these n's gets canceled with that. And if we want to calculate the standard error, well, that's the standard deviation of p hat. And so I can take the square root of the variance, and that's going to calculate the standard deviation of this distribution, which is what we call the standard error. So I simply take the square root of that, and now if I plug in the values for this problem, namely that n is 100 and p is 0.6, we can see the standard error is about 0.05. So what this tells me is if I pick a random sample of 100 students from CU Denver, I would expect the proportion of them that are undergrads to be 0.6 and with a reasonable amount of variability. So it wouldn't be that uncommon to get one that has a sample proportion of 0.65 or 0.55, since we see that it's not that unreasonable that things are going to vary by 0.05-ish. And as we did with sampling distributions for the mean, let's consider what happens when we increase the sample size. So we constructed this sampling distribution out of 100 students. And so one thing that we can see is from these formulas over here that as n gets larger, that's not going to affect the expected value of p hat. It's always going to be, we're going to expect to get a proportion which is equal to the proportion of the population. However, the standard error is affected by n. So as n gets larger, what we should expect is overall, the standard error should get smaller. And hopefully that also matches your intuition that the larger and larger the samples we pick, the less variability we're going to get in our sample statistics. And in the previous example, we were able to calculate the exact values of the expected value and the variance because we knew we had nice formulas for the underlying distribution, which was binomial. In many cases, we might not be able to calculate these quantities, the mean and standard error for the sampling distribution by theory, but we might have to use simulations to get approximations for them. So here's an approximation for the previous example. And if you're curious playing around with this, you can open up the R Markdown file that's posted in Canvas and recreate these plots and tweak them if you're curious about what happens if we change n, p, and how many samples we generate. So n here is 100, that's the size of our sample. P is the probability of a success, which would be how likely are we to pick an undergraduate student from our sample. And this is something that we can choose. This is going to be the number of random samples that we create. And the larger you do this, the more accurate it's going to be. And so what this code is doing is it's creating a vector where we're going to store all of these sample proportions. And it's going to run a loop 10 to the 5th times. Each time it goes through. What this function does, this is randomly going to pick a number from the binomial distribution, which has n equal to, in this case, 100, and p equal to 0.6. And this is telling us how many random numbers am I going to pick out of this distribution. So here, we're going to pick one number out of the binomial distribution that has n equal to 100 and p equal to 0.6. And then we're going to divide that by n. So this is kind of saying, let's randomly pick how many students in the sample of 100 are undergrads, and then let's divide that by 100 to convert that to a proportion. And then we store that proportion in this vector called results. And over here is a plot of a histogram of that. And so this was the mean of that value. So right here we can see that this distribution essentially is centered right at the population proportion, which was 0.6. And now we can calculate the mean and the standard deviation of this sampling distribution that we created using simulations. And we can compare these to the exact calculations that we had on the previous slide, and we can see that we expected this to be 0.6. Look, we're almost exactly there. And the standard error was 0.04899. We're just off over here. So we are getting extremely close approximations for the exact values when we run these simulations. And I would again direct you to that R Markdown file that I referred to on the previous slide to play around and see what happens when you change n to larger values. Does this match what we were able to derive from the theory? And we can see, yeah, all of these distributions have essentially the same mean, but the standard error is getting smaller and smaller as we increase n. And if you want to compare the expected value and standard error that we should get in theory to what we get from the simulation, then what we can see is the expected value is going to be the same we talked about no matter how big n is. But as we increase the size of n, we get that the standard error is going down and down and down. And we're calculating these, again, using the formula p times 1 minus p over n. So the p is the same in all of these calculations, but as n gets bigger, we can see the standard error is getting smaller. And if we compare this to the simulations, when we have samples of size 100, we're already pretty much right on the target. When we increase it to 200, okay, we're actually getting a little bit more accurate. And as we increase that to say 500, we're pretty much right on the money here. And if we go all the way out to 1,000, we're pretty much matching up with what we would get with the theory almost exactly. Okay, so now let's summarize all of these results in what's called the central limit theorem now for proportions. And so let's assume that x, random variable x, follows binomial distribution, and therefore the distribution for sample proportions can be written as how many successes were there divided by how large was our sample. And what we saw is that for larger values of n, these approximations for the expected value and variance get more and more accurate. And on the other end of things, for small values of n, these might not be good approximations. So the question is, well, how large does n need to be? And that depends not just on the size of n, but what the value of p is. So the conditions that we would want to check before we use the central limit theorem would be two things. I want to check that the sample size times p is greater than or equal to 10, and the sample size times q, the probability of a failure, is also bigger than or equal to 10. So in other words, the number of failures and the number of successes in my sample should both be bigger than 10. And provided those two conditions both are satisfied, then we get the following results. First is that the distribution, the sampling distribution for the proportion, is going to be approximately shaped like a normal distribution. The mean, the expected value of p hat, is going to equal the corresponding parameter in the population, which in this case would be the proportion of the population, which we're calling p. The standard error, we have a nice formula that we derived for that, which is going to be the square root of p times 1 minus p, all divided by n. And so to summarize this in one formula, what we can see is as long as our sample is large enough, the distribution for sample proportions is going to be normal. Its mean is going to be equal to the population proportion, and its standard error is going to equal the square root of p times 1 minus p over n. And so on the last slide, I just want to introduce the questions that you're going to have to answer on your reading quiz and just give you a little push in the right direction for answering those. So based on recent census, which we can imagine is for the population of the US, it showed that almost half of all residents in the United States' 5 largest cities speak a language other than English at home. So the precise amount was 48%. So let's imagine that a sample of 150 people are selected, and you might have a different value for n on your quiz. Are selected at random from these 5 largest cities. We want to calculate what is the probability that at most 40% of the people in that sample speak a language other than English at home. So we would expect our sample to have a proportion of about 48%. 40% is below that. Is this significantly below that? Well, let's use the central limit theorem to help us get a sense of that. So if we want to check to see whether, first of all, we can even use the central limit theorem, then what you're going to need to do is check both of these conditions. Okay, so it's not one or the other, but this is both. So I'll leave that for you guys to check on your homework or on your quiz. Then what I want to do is be careful that, say, if I'm going to calculate the probability that we would get a sample proportion that's at most 40%, so a proportion of at most 0.40, then I want to make sure that I'm using the sampling distribution and say not the binomial distribution to come up with a model for the distribution of sample proportions. So you want to use the standard error in here. Once you've got this distribution, then use the normal formula for the z-score. So I'm going to take my value, subtract the expected value, which in this case would be 0.48, and then divide by the standard error, which we can get using this formula. And then once we have the z-score, we can go ahead and use R to calculate what is the probability of getting a z-score less than or equal to this value. So you can use the standard normal distribution to calculate this. So give the quiz a shot, and we'll talk about this more in class.